Hey guys, and good morning. So, believe it or not, we're finishing this unit today. I know, sounds crazy. But as far as the instruction or material that you need to learn is concerned, this unit ends today. But after today, we'll start doing a lot of practice. We'll do a lot of workbook heavy practice and review. I'll assign a lot of progress checks and material from AP Classroom and more Khan Academy resources. Definitely plan to do your test on Friday next week and a quiz sometime, over the course of next week or this weekend. So yesterday we talked about a lot of stuff. We talked about conservative forces. We talked about gravitational potential energy. I hope you guys don't forget these things. But the most important things to remember from yesterday's lesson, number one, are this idea here that work is force times displacement, right? This is a very key idea in physics. If the force is acting at an angle, then it's force times displacement times cosine theta. The area under the graph of force versus displacement is work done. And I keep saying that every time you see a graph in AP Physics, some of the things you think about first are what is the area. And the area will always just be the y-axis times the x-axis. So check if that is something that is meaningful. Another key idea we talked about yesterday, I know you see a lot of writing here, but the important thing is here that kinetic energy, this in blue, kinetic energy is a half mv squared, and kinetic energy is the energy of motion. When work is done, energy is transferred. That's another very key idea we talked about yesterday, which is over here, that when work is done, energy is transferred. But also gravitational potential energy is mgh. This is gravitational potential energy. All work done by gravity is mgh. We talked about this yesterday. This is just review of the key ideas. Now, the other important key idea, and I hope I said yesterday, that this conclusion that the initial potential energy, the sum of the initial energy of a system is equal to the sum of the final energy of the system. This is the basis of the principle of conservation of energy, which is also a very key idea in physics and in science in general. This shows us that energy is always conserved, because what's happening here is we have kinetic work is done, and that work that is done leads to a change in kinetic energy. But if that work happens to be done by a conservative force, which gravity is a conservative force, then it leads to a loss in potential energy, which if you work the mathematics out, which we did yesterday, you end up seeing that the total potential energy of a system, the initial potential energy plus the initial kinetic energy, which you can call the initial total energy, because this will be the initial total energy of the system, will be equal to the final total energy of the system. Now this can be extended to multiple facets. What do I mean? What we have currently is that the change in potential energy plus the change in kinetic energy of a system is equal to 0, or more aptly or practically put, is that it's equal to a constant, because 0 is a constant number. So the change in potential energy plus the change in kinetic energy is equal to a constant, which means potential energy 1 plus kinetic energy 1 is equal to potential energy 2 plus kinetic energy 2 is equal to potential energy 3 plus kinetic energy 3 in all forms, and so on and so on and so on. Because the energy is conserved, this sum of the energy of the system will remain the same. Now this sum of potential, this idea of adding up potential energy and kinetic energy in physics is what we call the mechanical energy of a system, right? Mechanical energy of a system. There are other forms of energy, for example, thermal energy. It is not mechanical because it does not involve moving parts. There is sound energy. It is not mechanical. Heat, which is the same as thermal, not mechanical. But this is called mechanical energy of a system. So the total mechanical energy of a system, the total energy of a system is always going to be conserved. Now, we came to this conclusion by just looking at conservative forces. But what if non-conservative forces act on the system? And what are non-conservative forces? Well, just like you hear the word, non-conservative forces are forces that do not conserve energy, right? Non-conservative are forces that do not lead to, that dissipate energy from a system. Non-conservative forces dissipate or destroy, well, not destroy, dissipate energy or remove energy from a system. What that means is a non-conservative force, for example, friction, dissipates or removes energy from the system by turning that energy into something else or into another form like heat, right? So that is a non-conservative force. Another thing to note about non-conservative forces is that they are path dependent. Path dependent. A common example that is used is let me make this pen so big, or pen very big, yeah, cool. A common example that is used to demonstrate this is if I was erasing the work that I've written here, I would erase something like this. You know, if I want to figure out the work done on this path, right, by this non-conservative force of erasing, I would have to follow this entire path, right? So the non-conservative force is path dependent. But conservative forces, like the force of gravity is path independent. In other words, because we know that the work done by the force of gravity, now I need to make it smaller. The work done by the force of gravity is work done by Work done by gravity is equal to mass times acceleration due to gravity times height. So imagine you're climbing a set of stairs. You're climbing the stairs like this, and at the end of the day, you're going to be up here, where you have climbed, say, 10 meters, right? The potential energy you have here, the gravitational potential energy you have here, is going to be calculated by half times mass times gravity times height, this height here. It doesn't matter, even if these stairs were individually, let's say you moved 20 centimeters horizontally, 20 centimeters vertically on each stair, and and you're trying to calculate the potential energy you have, it doesn't matter what path you took to get here. Even if you had climbed spiral stairs instead of straight stairs like this, it doesn't matter what path you took to get there, the potential energy you have is the same, right? The potential energy you gain in climbing that height is the same. So that's why conservative forces are path independent, but not non-conservative forces are path dependent. So even in this very example, if I was trying to figure out how much work is done by friction when I'm climbing these stairs, I would need to look at all of these distances that my feet step on as I'm climbing these stairs. But gravity is a conservative force, so therefore it's path independent. So I hope all of those words just help to make that clear. Now, I said all of that just to show you that when non-conservative forces act on the system, then this equation has to change a little bit, right? Because we said that when a network acts on a system, it leads to a change in kinetic energy, right? And kinetic energy. And this network is work done by conservative forces, which leads to a change in kinetic energy. But when there's non-conservative forces acting on the system, then we also have to add work done by non-conservative forces, right? Because they also will lead to a decrease in the potential energy of the system. So the only application of this is this equation that we had earlier that said change in potential energy plus change in kinetic energy is equal to a constant, right? The only difference that exists is we will now add work done by non-conservative forces, right? Work done by non-conservative forces is equal to a constant. And what it looks like practically is you will have initial potential energy plus initial kinetic energy plus work done by non-conservative forces is equal to the final potential energy plus the final kinetic energy, right? That's what it will look like, because this work done by non-conservative forces takes away energy from the system. So the final energy of the system will be equal to what the initial energy of the system was minus the work done by the non-conservative forces. Yeah, this should be minus. I hope that makes sense, right? Because if a system has 10 joules of energy and then a non-conservative force like friction transfers 6 of those joules into heat, then you only have 4 joules of energy left. So you will have these 10 joules minus those 6 equal to the 4, which is the total mechanical energy left in the system. You're going to see how this works out in some examples that we're going to look at. Okay, the potential energy of a spring, I'm just going to dive straight into the equation for this one. The potential energy of a spring is called elastic potential energy because when a spring is compressed, right? Let's say this is a compressed spring. It has potential to, push outwards when it is released, and that potential is what we call elastic potential energy in a spring. The equation for elastic potential energy is just half kx squared. That's just how we calculate the elastic potential energy of a spring. So again, you will see, we will look at a lot of examples where we'll apply this, and then it will look or become more practical in that sense. So yeah, conservation of mechanical energy, I've kind of talked about this, that the total mechanical energy, the initial mechanical energy of a system, or the total mechanical energy of any system is always conserved. So the total mechanical energy, which is potential energy plus kinetic energy, this is initial plus or minus work done by non-conservative forces, because they take away energy from the system. So that's why this has to be a minus, is equal to the final potential energy plus the final kinetic energy. And the statement of conservation of energy, I think you guys have heard about it a lot, that says energy cannot be created or destroyed, but transferred from one form to another. That is the conservation of energy. Now, this work done by non-conservative forces for each situation will depend on what forces are acting on that system. If it is friction, you put here friction, which will be friction in most cases. If it's air resistance or sound or other forms, then that's what you put here as well. Efficiency of a system is the ratio of work output to work input. So work output to work input multiplied by 100. That's how we calculate the efficiency of a system, because you're trying to figure out what percentage of useful work is this machine doing, right? What percentage of useful work is this machine doing? And you calculate that by taking its work output divided by its work input. If its work output is equal to its work input, then this ratio will be equal to 1. Then that machine will be 100% efficient. But a lot of the times, actually, all the time in this practical world, all the time, there is no machine that is 100% efficient. So even these days, I don't know if you know, but the very first light bulbs were only 30% efficient. Only 30% of the energy input was coming out as light, and the rest was going out as heat. But these days, them light bulbs that are up to 70% efficient, so obviously that's an improvement. But yeah, don't forget this ratio, work output divided by work input times 100. And finally, power. Power is the rate at which energy is transferred. Energy, and we talked about how energy transfer happens when work is done, right? So when you do work, you're transferring energy. Let's say Solomon is pushing a crate, and Lovejoy is also pushing the same crate, not at the same time, right? If Solomon pushes that crate with a force of, 5 newtons, and it takes him 3 seconds to push that crate a distance of 10 meters, right? And then Lovejoy tries, and Lovejoy, I don't know what force, we don't know what force Solomon applies, but let's say it takes Solomon 3 seconds to push that crate a distance of 10 meters, and it instead takes Lovejoy 2 seconds to push that same crate a distance of 10 meters. Well, both of these people have done the same amount of work, right? Because they have moved the object the same distance, but one of them has done that work transfer faster because they pushed the same crate, which is probably 5 kilograms or 10 kilograms or whatever, but one of them has pushed it faster than the other, right? And that comparison in terms of how fast work is being done or how fast energy is being transferred is what we call power. So power is the rate at which energy is transferred. You guys like definitions, so I'll just write it here. Rate of energy transfer is power. And since it's the rate, and you guys know that every time someone talks about rate, you're dividing by time. So power is going to be work done divided by time. In short, power is force times distance divided by time. The units for power are watts, named in honor of someone called Watt. You can look him up, look at some of his accomplishments. But the units for power are watts, which is just a capital W. Now something else to look at this formula of power is, if I look at power is equal to force times distance, everything divided by time. If I kind of break this apart, because it's still the same expression, distance divided by time is still the same expression as we have here, but this distance divided by time, I hope you guys remember, is the same as velocity. So sometimes power can just be calculated by multiplying force times velocity. So yeah, those are two expressions that we can use to calculate power. Okay, so that brings us to the end of this unit. Crazy. And what we have to do next is look at practice problems, starting with just one problem that I want us to look at, and then in this lesson, then we'll look at some more tomorrow through the practice, the workbook. So let's say you have a roller coaster, and this is a very common energy problem. You have a roller coaster that is going like this, and then it's supposed to be flat, and then it goes flat. All right, and let's say that this roller coaster starts out at a height of 100 meters. This is 100 meters from the top to the ground. I can't draw straight lines. 100 meters from up there to there, okay? And you have a cart, or the thing in which you're sitting, you and your friends are sitting in this thing. Let's say it has a mass of 50 kilograms, right? Yeah, 50 kilograms. This height over here is, let's say, 20 meters, 40 meters, and this height over here is 50 meters. So let's label it. Let's call this point A, let's call this point B, call this point C, and call this point D when it's at ground level. We can use energy analysis to figure out the speeds of this object. We can start by saying, assuming there's no friction, we can use energy analysis to figure out the speed of this object at each of these positions, right? At each of those positions, we can use it to figure out the speed of those objects. Let's see how. We know that energy is going to be transferred in a system. As this object moves, it has potential energy at this position, right? It will have kinetic energy at this position, it will have kinetic energy at this position, it will have kinetic energy at that position, and it will have kinetic energy at that position. As it moves, this potential energy will be transferred into kinetic energy. But not only that, it will still have potential energy at each of these positions, because it has a height above the ground, right? Except here, where its height above the ground is 0, that's when it will have 0 potential energy. So what we know is that the initial potential energy plus the initial kinetic energy of a system must be equal to the final potential energy plus the final kinetic energy of a system. So we are going to use this equation at each position to figure out what we need to figure out. Potential energy we know is mgh, and kinetic energy we know is a half mv squared. and this will be mgh2 plus a half mv2 squared. So we can use this equation at any point to figure out speed, height, whatever of this object. So let's try to figure out the speed at point B. At point B, we need to first analyze where it started. It started at point A, and at point A it had only potential energy. So at point A it had potential energy, which was mass, which is 50, times gravity, I'll just use 10, times height, which is 100. And at point A, it is just starting, so it has no kinetic energy, so there's no motion yet, so the kinetic energy is 0. At point B, it has a height of 40, so same mass, same acceleration due to gravity, height of 40, and it also has kinetic energy, which will be a half times mass times v squared. So we have an equation in which the only unknown is velocity, so we can easily find that velocity as the square root of something. You guys go ahead and complete that, and I also want you to find the speed at C and the speed at D and submit your answers on Google Classroom. This will be all for today. Bye.